In this video, we're going to be going over partial fractions. Partial fractions is used in integration and summation in AS further. And essentially, it's like the reverse process of combining fractions, like with LCM. And what you're doing instead is you're breaking them down into their parts. So, for example, when you have 5 upon x plus 13 upon x squared, you do the LCM, right? And you combine them into 5x plus 13 upon x squared. So in partial fractions, you see that instead of just going from this to this, you can also go from this to this. It's like a reversible reaction almost. For partial fractions, it's just difficult seeing what form your decomposition should take. So that's what we're going to be going over. We're going to go over every single case you're going to see of partial fractions. So first, let's go over cases where the degree of the numerator is less than the degree of the denominator. This is like the most common type of case you'll see, and this is the most common case you'll see where the denominator has two linear factors. So here you break it down into two terms with one linear factor as the denominator of each term. So ax plus b, cx plus d. Let's do an example. Okay, 2x upon x plus 1, x plus 2. Let's write that as equivalent to a upon x plus 1 plus b upon x plus 2. What we're trying to do is solve for a and b to find the numerator. And the degree on top in this is going to be one less than the degree on bottom. And degree is like, means that the highest power in the numerator, the highest power of x in the numerator is less than the highest power of x in the denominator. So the first step we have to do is LCM, the right-hand side, to make the denominator the same. So 2x upon x plus 1, x plus 2 is equivalent to a x plus 2 plus b. I'm sorry about my handwriting. I don't know what that was. Plus b x plus 1 upon x plus 1, x plus 2. Since the denominator is the same, we can disregard it. And now we have 2x is equivalent to a x plus 2 plus b x plus 1. Since they're equivalent, you can substitute in any value of x and you'll get like the same expression on both sides. But like we can be smart about this and we're only trying to solve for a and b, right? So what we can do, okay, first let's solve for a. To solve for a, we want to get rid of the other unknown. And to do that, we can make x plus 1 equals 0. Because when this equals 0, this is going to become 0. So x plus 1 equals 0 when x equals minus 1. So let's use x equals minus 1. Then we get minus 2 is equals to a minus 1 plus 2 plus b 0. This goes away. We have minus 2 is equals to a. Now to solve for a, we're going to do the same thing. To solve for b, we're going to do the same thing, and we'll get rid of a. So x plus 2 equals 0, x equals minus 2. Substitute that in. Minus 4 is equals to a0 plus b minus 1. Minus 4 is equals to minus b, so b equals 4. And we have our answer for the numerators of both. So we've decomposed this. So 2x upon x plus 1, x plus 2 is equals to 4 upon x plus 2 minus 2 upon x plus 1. If you LCM the right-hand side, you're going to get the left-hand side. Now our second case is where the denominator is an irreducible quadratic. So here we have x plus a, x squared plus b, and you break it down into a upon x plus a plus bx plus c upon x squared plus c. Bx plus c is like the general form of a linear expression, and like the degree of the numerator here is 1 less than the degree of the denominator. So let's do an example. x squared plus 1 upon x plus 1 x squared plus 5 is equivalent to a x plus 1 plus bx plus c x squared plus 5. X squared plus 1, let's LCM the right hand side. X squared plus 1 is equivalent to x squared plus 5 plus x plus 1 bx plus c. The first thing I'm seeing is that we can get rid of this really easily. X plus 1 equals 0, x equals minus 1. Let's substitute that in. We get 2 is equals to a 6 plus 0 bx plus c. Now we don't have to deal with the b or the c right now. So 2 is equals to 6a. A is equals to 1 upon 3. To solve for this, b is the coefficient of x. We can plug in any value. So let's take x equals 0. We get 1 equals 1 upon 3, 5. 1 upon 3 times 5 plus 1 c. 1 is equals to 5 upon 3 plus c, which means c is equals to minus 2 upon 3. I don't think we can get rid of this, right? But now we have our a and we have our b, so we can just substitute anything in. Let's take x equals 1. You could take x equals 2, you could take x equals 5, you could take whatever. Now we get 2 is equals to 1 upon 3, 6, plus 2, b, plus minus 2 upon 3. Now let's solve this. 2 equals 2 plus 2b minus 4 upon 3. Cancel, cancel. 4 upon 3 equals 2b. 2 upon 3 is equals to b. Now let's write this out. That means x squared plus 1 upon x plus 1, x squared plus 5 is equals to 1 upon 3 x plus 1. Let's take 2 upon 3 common. So plus 2 upon 3 x squared plus b, x squared plus 5, sorry. And in our numerator, we have x minus 1. Okay? Now in our third case, we have the denominator contains an irreducible quadratic. No, we don't. Sorry, we have the denominator contains repeated linear factors. Okay? So here, we break this into 3 distinct terms. A upon ax plus b, our first linear factor, plus b upon cx plus d, plus c upon cx squared plus d. Cx plus d squared. Oh my god. Okay, what confuses people in this is this term. That why is this like this? Okay, it's confused me many times. So, okay, when we break this down, right, usually, we see it as a rule that our numerator is 1 degree less than the denominator, right? So a upon ax plus b, we have that. And this would be like bx plus c upon cx plus d squared. When we break this into terms, like bx upon cx plus d squared plus c upon cx plus d squared, we have bx upon c squared x squared, right? This x is going to cancel, but there's obviously nothing in the numerator here for this to cancel with, right? The x in the numerator here cancels, so we just get a upon ax plus b upon cx plus d plus c upon cx plus d squared. Okay. Our final case is where the degree of the numerator is equals to the degree of the denominator. This case doesn't show up that often, but it's useful to know. So here we break this into three distinct terms. So a plus b upon x plus a plus c upon x plus b. Let's do an example. X squared upon x squared minus 16. So we can turn x squared minus 16 into x plus 4, x minus 4, right? Now to break this, we put in that form a plus b upon x plus 4 plus c upon x minus 4. Our first step, as always, is LCM. X squared is equivalent to a, x squared minus 16, plus b, x minus 4, plus c, x plus 4. Now we just substitute again. So we can get rid of this by doing x equals 4, which will also get rid of this. So x equals 4, 16 equals a 0 plus b 0 plus 8c. 8c is equals to 16, which means c is equals to 2. Now let's solve for b. When we substitute in minus 4, we get rid of c and we get rid of a again. So 16 equals a 0 minus 8b plus 0. 16 equals minus 8b. b is equals to minus 2. Please comment if I'm making a mistake. Now we can just substitute in any value. Let's take x equals 1. You can take 0 too. So 1 equals a minus 15 plus, minus 2 times minus 3 plus 2 times 5. So 1 equals minus 15a plus 6 plus 10. Minus 15 equals minus 15a. A equals 1. So we found our values. And we can write this as x squared upon x squared minus 16 is equals to 1 plus 2 upon x minus 4 minus 2 upon x plus 4. Okay. And that's partial fractions. Basically, once you get the form right, it's just algebra. You just need to memorize this, understand the logic behind it. You just LCM, then you substitute, then you solve. Let me know in the comments if you guys have any questions, any suggestions, anything. You can send in questions from any chapters you want to solve, whether it's from AS Further, AS Math, A-level Math, maybe I can try. O-level Add Math, O-level Math, whatever. Anything you guys want to solve together, you can send it on WhatsApp or Instagram. Please like, please subscribe, and see you next time.